All right. So last time we ended on a very weird and abrupt note. Welcome back, everybody. Happy Garbage Day. Because my microphone decided just to die. And of course, it could not have been more perfectly timed. I was telling you that I was contractually obligated to keep talking, and then my microphone's like, no, you're not. So I think I figured out what went wrong. The laptop that I'm using only has one port to plug things into. So I have like this extension thing for all of my devices, and I had my microphone plugged into an extension of an extension that was plugged into my monitor, and I think that was too many extensions. So I have my microphone plugged in as directly as I can to my computer this time, and so far so good. But if I suddenly start screeching, please tell me. And I will shut off this microphone and just use the one that came with the laptop, and we'll try to make that work. But I am contractually obligated to keep talking, or at least to give it a shot. Thanks for being willing to switch to Zoom today. As you can tell, I'm doing relatively okay, but projecting to a classroom is just not in my wheelhouse right now. And plus, no one wants me to cough all over them and make them sick. So I'm going to cough all over my desk at home, and we'll make it work. Let me share my screen so you can see what we're looking at. See, I remember to do that in this setting since we're all on the same page here. I wanted to start with formative assessment number 4, which I read through all of your answers this morning and updated grades accordingly. Speaking of work to do, you also have homework 3 that is out right now, and I believe that is due in a week. Does that sound right? That's the next thing that'll be due, I believe so. Took a look at the database, and it looks like not a lot of folks have started, but homework 3 you know everything you need to know to be able to do that. And after today, you'll know everything you need to know to do homework 4, which is going to be on counts. I'll let you know when that's ready. Just to put a pin in what's coming after that, within the next week or so, I'm going to get you information about homework 5, which is going to be different. The goal of homework 5 is for you to take data that you care about and practice using at least one of the models that we talked about to predict a generalized outcome. So I will give you some parameters and a little bit of guidance, but ideally it would be a project that you already wanted to do, data that are meaningful to you that you're already working on for your research, so that you can essentially get free statistical consulting by submitting a homework and getting my feedback on it. So that will be an individual data assignment. You will do your own writing for that, and you will get a chance to do a revision on that. That would be due at the end of finals week. So that's still several weeks away, but I just wanted to remind you that that is out there as what homework 5 will be. Let's see here. Any questions on logistics or due dates or stuff to start off with? So far, so good. Is my microphone screeching, or are we still good? Still good? Okay. Excellent. Should we talk about formative assessment number 4 then? Thank you for the thumbs. I appreciate that. So I looked through these, as I said, a few sources of common confusion that I want to make sure that I clarify. And if you have questions as we go, please put them in the chat, or you can use your voice and talk to me as normal. So first question is, what is the role of a log link function, and what kind of outcomes would you pick a log link for? What do you think, folks? What is a log link function designed to do? What is a log link function, and when would we use it? That's the question. I'm eagerly awaiting your responses in my ears or in the chat window. Your choice. All of you got this right. There's no need to be shy. I'm starting off with a softball here. Log link is for counts. Yes, it is. That's the unit we're in. Yes, indeed. And what makes a log different from a logit in terms of what it does? Because they sound kind of the same. And logs are involved in logits. What makes a log link function different in what it does than a logit? Slope shut off at 0. Yes, so that is for log. The idea of a log is to create a boundary at 0 so that predicted counts stay above 0 as they should. Inverse link to an outcome at or above 0. Yep. So the link function is the log. The inverse link is the unlog, as I would call it. If you exponentiate it, then you get back to predicted counts. And there's only one boundary. That's the key idea here. So I actually had a question about this. Since I keep all my stuff online, I get a handful of questions every week from just random people on the internet who've stumbled across my course materials and they want my help. And I got a question from someone just last week that had used a negative binomial model with the log link function to predict a count. And in this person's data, the highest count was 26 that they observed. And in the model, though, they ended up with predicted counts that went above 26. And the person was like, how can that be? So would anyone like to guess what my response was? So they used a negative binomial distribution with a log link to predict a count outcome. The highest predicted count they had in their data was 26, but the model generated predicted counts above 26, and they were like, is that a problem, or why did that happen? So you play the consultant, folks. Did they remember to inverse link? I'm guessing that they did because they were referring to Stata code. And in Stata, when you ask for margins, it inverse links for you by default. That is important to remember, though, that the model is predicting log counts directly, so you need to inverse link the predictions to get back to regular counts. Well, let me phrase the question differently. Is it necessarily a problem that the predicted counts went above 26? Question, were there too many or too few zeros? Could have been. They didn't mention that aspect of it. But the too many or too few zeros would not be related to why the predicted counts went above 26. Is that a problem? Got one vote for not a problem, one vote for is a problem. Does a log link have an upper boundary? No. No, the log link doesn't care. It stops at 0 and it lets you go up into positive infinity. So you can have a log link that predicts, a count of 1,000,000. And that's not necessarily a problem. My answer to this person was, well, that the link function isn't designed to cap the positive end. It's designed to cap the negative end at 0. If you were worried about capping the positive end, then you need a different kind of link function, such as a logit, and I saw an answer about that just a second ago. A log link goes from 0 to positive infinity. In the expected count, it's negative to positive infinity in the log scale. That is true. And in logits, the probability ranges from 0 to 1, whereas the logit itself ranges from positive to negative infinity. All of that is correct. So if you were worried about having an upper boundary that you wanted to stay within, a log link isn't going to give you that. Do you know of something that would? I'll give you a hint if you add 2 letters to it. Logits, yeah. Our friend the logit. Logits are designed to keep things within 2 boundaries, an upper boundary and a lower boundary. By default, those boundaries are 0 and 1, but you can always transform any kind of outcome variable into a proportion that ranges between 0 and 1, where 1 would be like the 26 in this person's example and 0 would be the 0. So if you're in a situation where you have to worry about predictions exceeding an upper boundary and a lower boundary, then you don't need a log. You need something else, such as a logit or a probit. I bring this up because the next unit that we're going to do, we're going to get our friend logit back because we're going to be focusing on things like percent correct. Percent correct is also bounded. If you have the proportion of correct responses, that's bounded between 0 and 1. Logits are going to be used for that. The only catch is that a proportion is a continuous variable, and so we need a different kind of conditional distribution besides Bernoulli or multinomial for that. So putting in a plug for what's coming up next. Anytime that you need a boundary at 0, a log can do that for you. But if you need 2 boundaries, then you've got to do something else, such as a logit is the one answer that we know so far. So several of you wrote that you would pick a log for count outcomes and you would pick a logit for categorical outcomes, and all of that is correct. But I think the more general principle is it a one-sided boundary or a two-sided boundary? And categorical data is a discrete distribution where we want to make sure that each submodel stays within its 2 boundaries of low and high, 0 and 1 for the lower case or the uppercase. So my answer then, to wrap up, the fact that it predicts a count above 26 is not necessarily a problem. Theoretically, the count can go on forever. You just haven't happened to observe any counts beyond that point. Okay, any questions on that or clarifications I can make? That is one thing, that the idea of inverse link, that's one thing that can be very tricky when you're managing your output, particularly in packages that spit things out sort of by default in different metrics. Like if you're looking at stata output, it can be very tricky to figure out if you're looking at, say, a log metric versus an odds ratio metric versus an expected count metric. So make sure you know what the scale is of the piece of output that you're looking at, because some pieces of output default into each of those metrics, and it can be confusing to go back and forth when the numbers don't match. So in count data, we still have something like an odds ratio, where if you exponentiate the slope that's in logs, you unlog it, basically e to the log slope, that is called an incident rate ratio. And that functions like an odds ratio in terms of an effect size, where negative slopes are shoved between 0 and 1. 1 for the incident rate ratio is a slope of 0, and then positive slopes go from 1 to positive infinity as well. Okay, question 2 then. For what kind of outcomes would Poisson and negative binomial conditional distributions be appropriate? Here's another softball. What would we use Poisson or negative binomial for? What kind of outcome? This isn't even a softball. This is like t-ball. This is like the ball is sitting up on the tee and you just have to swing the bat at it and not knock the tee down. What kinds of outcomes would you fit a Poisson or negative binomial distribution to? People on the internet, I have my bat above my shoulder and I'm waiting to hit the ball off the tee. That's what's happening right now. Counts, yes, exactly. That's what we're talking about. So these are discrete distributions, meaning that they understand that counts can only be integers, whole numbers, and they are designed to capture a distribution where the lowest value you can have is 0 and the highest value you can have is some positive integer, positive infinity. What's the difference between the two? Which one is nested in which other one? Let me start with that way, because one of them is a nested model relative to the other in terms of what it says. This is not a t-ball question. This is more like, I wouldn't say coach pitch. I'd say it's still softball. We got 2 answers, negative binomial nested in Poisson. I would actually phrase it the opposite way. So negative binomial adds something to Poisson. It adds that stretchy extra dispersion factor. So if you don't need a stretchy extra dispersion factor, if that factor is estimated as something close to 0, then that simplifies as Poisson. So Poisson is actually the simpler one in those cases. In the Poisson distribution, the mean and the variance are supposed to be the same thing. In negative binomial, the variance is allowed to exceed the mean in different patterns. The one that people have sort of settled on as working relatively best seems to be what's known as negative binomial 2, which is a quadratic function of the mean. So I had a few folks write down things about this idea that the mean and the variance are the same. There's not only one mean. So if I fit an empty model, if I don't have any predictors, then there is only one mean. I have beta 0 as my intercept. That's my best guess for everyone's score, and it's the mean count across the entire sample. But once I start adding in predictors, then I get a different conditional predicted mean based on whatever values of the predictors I have. So there's many possible means that are created by including predictors in the model. And the idea of Poisson is that at a given level of prediction, the variance is supposed to be the same number. So if my combination of predictor values creates an expected count of 5, then there's supposed to be a variance of 5 around that predicted count of 5. There's supposed to be a variance of 6 around a predicted count of 6. So there's not just one mean. It's conditional on how complex your predictor model is. There could be a bunch of different possible values. So it's only one mean in an empty model when you're just talking about sort of like the naive distribution without any other additional information coming into play. Each of these then ranges from 0 to some positive count. And what are the two concerns related to zeros that we need to watch out for? This one's more like coach pitch. So picture a parent standing in front of a little kid, tossing the ball as gently as they can. What are two concerns related to zero values that we need to worry about? Too many and too few. Ding, ding, ding. Yeah, so no zeros is one problem and too many. Exactly. So every count distribution is expecting at least some zeros. If zeros are not possible, then we need to change it into something that is called either a zero truncated or zero altered. So the acronyms for that are ZTP for zero truncated Poisson or ZAP for zero altered Poisson. Those are synonyms. So you can ask the Google about one or the other and get to the right spot. And that is a special case of a Poisson or a negative binomial. There's zero altered versions of each where they don't expect any zeros. And when I first learned about this, I was like, well, I can fix that problem. I'm just going to subtract 1 from all the scores, and then ta-da, now I have zeros. It turns out you don't get the same answer doing it that way, so I would not recommend. The idea is that they change the total area under the curve, so to speak, the total amount of like what's possible in probability to subtract off the part that 0 would have had. So the remainder above 0 still sums to 1 in terms of the total area. So that they take off that part. When you would need to worry about that is when you're collecting a count where by definition something would have had to have happened once in order to make it into the data set. So the example that I gave in a previous class, if you're looking at, say, hospital archival data and you're studying the number of days that someone spends in a hospital because of whatever condition, in order to get into the hospital database, they would have had to have been there at least one day. So there's nobody in the database who never went to the hospital by definition. So that would be a case of zero altered or zero truncated. That is going to be used as one way to deal with the other problem, which is extra zeros. When there's more zeros than what the Poisson or negative binomial distributions expect. And that was the thing that I was starting to talk about last time, and my microphone lost its will to live, and it shut me down. So far, so good, though. So that's question 3, which we're going to talk about today, and fill in the gaps in that, what to do with too many zeros and what your choices are. There's 2 different choices, and there are different situations in which you might prefer one versus the other, so we want to go over that. So I will save question 3 for later, and I want to make sure that we get to question 4 because there was a lot of different answers to this and a lot of potential misconceptions. So when you originally learned like linear regression, at some point you were told that certain things had to be true about the residuals for your model results to be believable. The residuals, so the part of y that is left over, the idea of residuals, by the way, is synonymous with the idea of conditional distribution. Conditional distribution, I think, is a more general term for when you don't usually work with residuals as having a separate estimated variance. But the idea of residual distribution or conditional distribution, or the part of the outcome that's left over after the predictors have had their say, that's what we're focusing on. So you were taught that the residual distribution, the conditional distribution, the E's were supposed to be three things. They were supposed to be normally distributed, they were supposed to have constant variance, and they were supposed to be independent. And so the question is, which of these things have we changed and which of these things is still the same? So the easier one to focus on, normality. Do we always have to say that the conditional distribution is normal? We're back to T-ball again. Yeah. Waiting to hit the pitch here. Do we always have to have normal residuals? Certainly not. Indeed, that's what this whole damn class is about, is no. Normal residuals are not going to happen for certain kinds of outcomes. Outcomes that are not continuous, outcomes that are not numbers. We started with binary and categories, right? There's no way those residuals can be normal. So if normal is not plausible, we can pick a new distribution to use instead. But what tends to happen is that this idea of normality and constant variance, they go together. So the normal distribution is one of the few that I even know of that has a separately estimated variance parameter. The other ones, the variance and the mean, are somehow tied together. So just to review, if you have a Bernoulli distribution, that is a distribution where only zeros and ones are possible. We do that for binary outcomes. That one says that the variance is conditional on the mean. It's the mean times 1 minus the mean. And it's the same idea, there's not only one mean, it's the conditional mean. So if my predicted probability of a 1 is 0.6, then the variance around that is 0.6 times 0.4. If my predicted probability of a 1 is 0.3, the variance around that is 0.3 times 0.7. So the variance and the mean are tied together, but they're tied together in a way that they're not constant. There is no one estimate of variance that you can use that's going to hold all the way across the line, because the variance has to shrink the closer you get to the boundaries. So we're changing normality and constant variance at the same time in most of these cases. If we go to Poisson, then it is the variance and the mean are supposed to be the same. That means the variance changes as the mean changes. In negative binomial, the same is true, but the variance changes quadratically as a function of the mean, not just as a one-to-one correspondence. So in picking a generalized model, in picking a different distribution, we are changing normality and constant variance at the same time into something that is more reasonable given what possible values the outcome could take on. So what is reasonable depends on what is the scale? Can you have a negative count? No. Okay, that means normal is not going to work up to a point. Can you have values in between? No, that means you need a discrete distribution if it's not truly continuous. So does that much make sense so far, the idea that normality and constant variance are tied together? One thumb. Have they put in a thumbs down icon yet? Can anyone check? I had been using poop emoji for thumbs down. But there's a no sign, right? There's like a crossbar thing that's like no. I think someone found that. Oh, there is a thumbs down. Excellent. No more poop emoji. Although I have to say, it makes me kind of sad to see all the upside down thumbs, but I know I asked you to put them on. Oh, poop emoji, there we go. See, the poop emoji is happy. It's like, yeah, I'm not understanding, but I still have a smile on my face. Or as my son called it when he first learned about that, moji poop. He used to come home with cookies from the grocery store decorated like feces. It's like, why? Who thought this was a good idea? Oh my goodness. Feces cookies, no thank you. I know, it's hysterical, but it's like, how can you eat something that looks like that? So maybe no poop emoji. They put a thumbs down icon, that's good enough for me. But I bet they don't have thumbs sideways. I bet they don't. You're forced into a binary decision of your thumbs. So normality and constant variance, conditional distribution. Now, what about independence? So first, let me clarify. Oh, thumbs pointing. That works as thumb sideways. Excellent. Okay, Zoom. It's come a long way. And you can point left or right. Like, I'm with that guy, that kind of thing. Like, you know, those t-shirts with the thumbs. It's like, anyway, independence. Back on track, Lise. Independence means independence of observations, meaning the residuals for any pair of people are no more related than for some other pair of people. So that depends on your sampling design. That is not a statistics problem per se, that is a sampling issue. Can you think of some examples in which you would not have independence and instead you would have dependence? You would have a relationship between the residuals of certain observations more than others. Can you think of examples of sampling designs where that would be true? Longitudinal things, nested things, yep. All the other classes I teach. Yeah, so if I have the same people measured repeatedly, the E's from the same person are probably going to be more alike than the E's from different people. In a setting where people are part of naturally occurring groups, if I sample students from multiple classrooms or children from multiple families, the people from the same, it's called cluster in that sense, the people from the same cluster are going to have residuals that are more alike than people from different clusters. So this is a sampling issue, and it would not be reasonable to pick a model that says, no, 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 everybody's supposed to be independent if you know that you did not sample them that way. Another instance of this, items on a test. If you're trying to measure an ability of someone with multiple items, then you can think of that as another case where items would be, item responses are nested within persons. And my ability would cause a relationship between the residuals of different items. So that's another context in which you'd see this. So let me phrase the question then. Does anything that we've talked about this semester change that assumption that we're dealing with independent observations? Couple votes for no. That is correct. Nope. This is still independent. These generalized linear models that we've been working through are for designs in which people are supposed to be independent. Now that means that if you have a situation that doesn't work with that, you need something else to add to your generalized linear model that allows certain residuals to be related. Turns out that is what multi-level modeling is for, or what is known as mixed effects modeling or hierarchical linear modeling. Very briefly, in those models, the key thing is that we don't just have one kind of residual. We have one kind of residual per dimension of sampling. So I would build in like one type of E for differences between clusters and another type of E for differences across people from the same cluster. So you're separating out variance that's predicted and left over per dimension of sampling. That's how those models work. The reason that I'm putting this in here is not just to make sure that we recognize that these models are still designed for single levels of sampling kinds of designs, but also to foreshadow how the models that we're going to turn to later in about a month or so, maybe less, maybe 3 weeks, multivariate models differ. So we have one more unit of generalized, unit 4, and then unit 5 we're switching to the idea of multivariate, and how would we address a situation in which each person has multiple outcomes, for instance, or dyadic data or family data where I might have a parent outcome and a child outcome, and I want to look at how those are related to each other and what predicts each. So in those kinds of designs, we have to do something different that allows residual relationships where appropriate based on the fact that these units come from the same something, same person in longitudinal, same cluster. So we're still dealing with independent observations in this context. That's the take-home message here. And I think that's it. Yeah, that's the last question. Okay. Any of that you want to ask me about or hear differently? Nothing. Okay. I'll take that as a no. And I'm going to close this out, and I'm going to head back to slides. That's where I want to head. So we're going to talk about the extra zeros and the no zeros problem that I was going to talk about last time, and then my microphone died. Okay, microphone, are you listening to me? This is your last chance to interrupt me, because I'm going to get through this come hell or high water. You hear me? Okay, it's not saying anything. So far, so good. I am on slide 13 of lecture 3 then. That's where I want to pick up. So if I'm in a situation where I have a count with no zeros at all, then I need to modify my Poisson or negative binomial to make it zero truncated or zero altered. And there's variants of both kinds. So you can have zero altered Poisson or negative binomial, where the difference is the stretchy factor that allows negative binomials variance to exceed the mean, same as usual. The other thing then, extra zeros. So this is the new part we haven't talked about yet. There are two main ways to deal with the extra zeros. One of them makes them a focus, and one of them makes them a nuisance. First is nuisance because it is more common and it's built into more software packages more readily. So we can use what is known as a zero inflated Poisson or negative binomial, which is what it sounds like. There's an inflation, there's an extra amount of zeros relative to what is expected. So expected is the key here. Every count distribution expects some degree of zeros, fewer as the mean moves off of zero, but some to some extent. So this is an option for when you have extra zeros relative to what would be expected just based on the regular Poisson or negative binomial distribution. And the idea is to create a second submodel that predicts the probability of being what is known as a structural zero or an extra zero. So this type of idea is motivated by thinking about the count as describing two qualitatively different kinds of people. So for instance, if I asked you, how many cigarettes did you smoke this week? People who do not smoke ever are going to say 0. And they would always say 0 because they don't smoke. Like they're not really part of the population of smokers that we would want to focus on. Some people who do smoke might say 0 because they didn't happen to have smoked this week, but they might smoke next week or they might have smoked last week. So if we think about these two qualitatively different groups of people coming together to make one distribution, what is likely to happen is that there's going to be a huge pile of zeros where some of them are from people who would never ever smoke, and some of them are for people who just happen not to smoke during the time period they were asked about. So the idea of this is not applicable to me, like I am always going to be a 0 no matter how you ask me the question, that's the idea of a structural 0. Like this behavior, this question is not relevant to me. And that's the way that these models are motivated. So in this case, what we're going to do is build one model that works like usual, that has a prediction of all the counts, including all the zeros. So we might predict, and I have a subscript of C for saying this is the count part of the model. I might put in my X predictor and ask the question, as X goes up, does my count go up? Okay, cool, no problem with that. Here's submodel 2. This is focusing on treating one's propensity to be a structural 0 as a separate but simultaneous binary outcome. This is what's known as an inflation model more generally. It shows up in a couple different contexts, and it's the idea of dichotomizing whether you are an extra structural 0 or you're not. And so the logit link is now going to be used along with the Bernoulli distribution to predict this binary outcome. What is the probability that you are an extra structural 0 relative to what the count distribution expects? So this makes good sense, like theoretically, I think. Like we can think of count outcomes in which, yeah, there's just some people for whom this is not applicable and they're structural 0s. But where this falls apart is on the ground. Here's the critical distinction of what makes this approach different than the one I'm going to tell you about next. Zero values are in both of these submodels. What does Z stand for? That is the subscript I'm using to say this is the intercept of the zero inflation model as opposed to the intercept of the count model. These are two different beta zeros because these are two different submodels being estimated simultaneously. Zeros are in both of them. So if all you have for a person is their count of 0, there is no way to definitively say, oh no, this 0 is expected, but this one's extra, because they're both 0. They're the same. So I think that's where this kind of falls apart is, let's say that you find a significant predictor of being an extra 0. Well, how do you know which zeros are extra and which ones are expected? You don't. All you know is the amount of zeros that the count distribution would expect, but you don't know which zeros are expected and which aren't. So to me, this is weird in terms of trying to interpret it. What happens in some cases at least is rather than trying to put predictors in the inflation model, they just estimate an empty model. They let an intercept be here saying, yep, there's just some extra zeros. We're going to let them just be there. We're not going to try to predict them. We're just going to account for them so that the rest of the model is more accurate. So that's one choice. So in this approach, in order to figure out what a person's expected count would be, you have to put the two submodels back together again. And so you end up with the expected count from the count part of the model, but then you have to downweight that with the probability that they are a structural 0. So here's the math by which these things get put back together again. You have your expected count given by mu, and then 1 minus the probability that you are a structural 0 as a multiplier of that. So it's like if I have an expected count of 5 from the count model, my predicted y is not 5. It's something less than 5 because I also have to know what is my probability of being a structural 0, and it's going to downweight that 5. So if you fit these sorts of models, you have to be careful to make sure that whatever software or algorithm you're using for prediction understands that you got to put them back together again to generate an expected count. There are, let me skip the second part here and give you a picture because I think this is easier to talk about. Then we'll do the second one. So this is a picture that I stole from an article published in 2007 in the Journal of Family Psychology of all places. It is a tutorial on count models. But I really liked this picture, and so I stole it, and I borrowed it, let's put it that way, and added some stuff to it. So what they are showing here is an example outcome of the number of steps a couple has taken towards divorce, which apparently ranges from 0 up to about 12 or so. So if we put on our expected versus unexpected hats to think about what a 0 could be, one type of 0, a structural extra 0, would be like, how dare you ask me about how many steps I've taken towards divorce? I am happily married. I would never. Jonathan, if you're listening, that's my answer. You can quote me on that. I would never. I would never take any steps. I am a structural 0. I am happily married. Yay me. There may be other people in the sample whose lives are not as wonderful. And they're like, I haven't taken any steps towards divorce yet. I haven't gotten around to it, but I'm going to. Like, it just happens to be a 0, but I'm part of the population that sees myself heading towards divorce. So the trick is trying to figure out within this pile of zeros then, like who's who. There's no way to pull that apart. All we know is the number of extra people that are in this pile that shouldn't be if the data actually followed a Poisson conditional distribution. So the gray line here, the first one with the circles, that's this right here. So if you watch my mouse, the predicted number of zeros from the Poisson is really low, and the Poisson predicts there'd be way more 1s and 2s, and then it kind of captures the curve decently well. But if you look at the gap between what Poisson says right here and the number of 2s, like, it's clear this doesn't fit. If we go to negative binomial, as the dashed line here, sort of in dark gray, that's this one. It starts here. So it does a better job of accurately representing how many zeros there are, but it still thinks there's way more ones and twos relative to what the rest of this distribution look like. So it's over predicting the number of low counts because of these extra zeros. The zero inflated versions of these distributions are like, you know what? I can fix that. I'm just going to fill in the gap from the probability of a zero that's expected from the Poisson, like right here, all the way up to what it is in the data. And I'm just going to say, you know what? Your probability of being a structural zero is the difference between how many I have and how many the Poisson thought I should have. Cool. That's it. Negative binomial, the number it thought it should have is right here, and it's going to fill in the gap to create an inflation model for however many it takes to get from where it was supposed to be all the way up to the top. So it's working mathematically with just this idea that there's supposed to be this many zeros according to the distribution. The inflation model is just going to bring us up to however many we happen to have. So the math isn't nearly as elegant as this idea of structural zero, because if someone wrote down zero, there's no way of telling definitively if they're always going to be a zero or if they happen to be a zero this one time. Okay, does that make sense so far? I can only see one of you, the TA who's had this before, and since I pay him, he has to nod and say it makes sense. There's some thumbs.
I have a question.
Please.
You said when they write down zero, it's no way to differentiate if it's actual zero or it's just happened to be zero. But I feel when we're doing the survey, like, so for example, if you're doing the step taken towards divorce, aren't you usually will ask, are you happily married? Have you ever think of divorce? Or is it just directly go step taken towards divorce? So if you add one extra question to clarify, like to differentiate, like, are you a smoker? Like, yes, no, then you reroute. So then you won't have the problem of this, right?
Yeah, and that's what you would put in the inflation model to try and solve this problem, is any other piece of information you have about a person as to how likely it is that they're a structural zero, that would go in the inflation model. Potentially, it could go, the same predictors could be used in the predicting the count as in predicting the logit being an extra zero, but not necessarily. But so yeah, that's what people would try to do if they were really focused on differentiating these two. It's really a mixture of two populations, is to try to pull in extra information that could tell us what kind of zero someone is.
Yes, thank you.
But you never know if you're right? It's all probabilistic, and you'd have to make an argument sort of theoretically that, after I control for X, Y, and Z, I know the probability that someone's in structural zero. So this type of zero inflation model, go back a couple slides here. Option 1. So a zero inflation model, it treats being an extra zero kind of as a nuisance, in that you can just allow them to be there and not predict them, or you can try to predict the logit of being a structural zero. But you have to keep in mind that the count part of the model still has zeros in it too. So you're predicting a value of zero in two different places simultaneously across these two submodels. The alternative is to simplify. So the other option, number 2, on slide 16 here, is what's known as a hurdle. And for those of you who ran high school or college track, yes, it is that same word, the idea of the thing that you have to jump over to get to where you're going. It's called a hurdle model. And this is based on the idea of not differentiating kinds of zeros and just splitting the data. So this type of model I tend to talk about informally as an if and how much model. So the two models that we have in a hurdle model, one is that we only predict the positive counts. So counts of 1 to whatever are predicted in one submodel, and I call that the how much part. Like, you're part of this population, you have a score of at least 1, how much do you have? And because we don't have any zeros in this part of the submodel, we have to use the zero altered or zero truncated version of the Poisson or negative binomial. So the same strategy that we would use if we didn't have any zeros, we borrow to solve the problem of extra zeros in this context. So we take all the zeros out of the count and we put them in a separate submodel. So I'm using H as a subscript here for the Hurdle submodel. So this gives you the prediction of the logit of the probability of having a zero of any kind. Zero at all. Not extra versus expected, just at all. And so the submodel 2 is the if, like do you do this behavior at all? Yes or no? And then if you do this behavior, how much? So to me, if you have a mixture of populations that is qualitatively different, I see this as being more useful. Let's say that you're trying to run, like you're doing an intervention design and you're trying to reduce, incidents of negative behavior. So for instance, you're trying to keep people from using, drugs that are really bad for you, like, heroin, cocaine, bad stuff like that. You might not take someone from being a severe drug user into a non-drug user, right? They still might be a user, but you might be able to reduce the amount of drugs or how frequently they do it, or other types of parameters within the use category. So if I applied this type of model to something like drug use, it would be submodel 2 is, are you a drug user? Like, do you anything beyond 0? And so this would predict the probability of using drugs at all. And then the count part would predict the number or the frequency, whatever the count represents, of drugs in users specifically. So you're separating out the two populations into two parts, if you do the behavior, and then how much if so. So I like this one for certain kinds of outcomes in which the shift from 0 to 1 is a qualitatively different shift. Not just one more, but it's like the presence or absence of a behavior. This can solve problems of how to deal with other things like, let's say, history of child abuse. You give a scale that's designed to measure, childhood maltreatment experiences, for instance, on a continuous measure. You have multiple items like how often did this happen, how often did this happen, how often did this happen, something like that. People who were not maltreated are going to answer 0 to everything. People who were maltreated are going to have some score above 0. And it's often the case is like, well, how do I treat this variable when it's kind of like two different kinds of people? Well, you can literally carve them into the two kinds. You can predict what is the probability that someone was maltreated at all, and then what is the severity of that maltreatment as indicated by the count part of the distribution. So the hurdle models are specific to counts, but there's also analogs in continuous distributions as well. They're known as two-part models. And the continuous part could be replaced, the count could be replaced by some other continuous distribution, such as even normal or log normal or something like that. So this idea of divide and conquer for the extra zeros, for the any zeros, it shows up beyond just count data is what I'm trying to say. So zero inflated. These tend to be a little bit harder to find. You can always do a sort of a shortcut and just literally carve the data up into two different variables and predict each variable separately. You would lose the capacity to do any kind of joint hypothesis test or comparison, but that may not be of interest and you may be willing to live with that. So those are the two choices. So a hurdle would just chop this right here and be like, are you in this pile or that one? And if you're in this one, how far are you? So those are the two ways to deal with zero inflated counts. Mr. Microphone, thank you for not dying on me. All right, how are we doing? One thumb, one nod. So how would you know that you need to worry about this is a question. So whether or not we need a negative binomial over a Poisson, most people agree can be done with a likelihood ratio test. We fit each model, we see which one made the data taller. If it's enough taller, we keep the one with extra parameters. Whether or not we need a zero inflation model is somewhat up to debate as to how you can tell this. Some people say that you can use a likelihood ratio test in the same way to test whether the inflation model makes the data significantly taller. There used to be this thing called the Wong test. That tends to be used to compare predictions across different kinds of distributions, and there's some debate about whether you can use it for this purpose. Current thinking is no, previous thinking is that you can. But you can always look at AIC and BIC so long as your models are all sort of within the same family. So I wanted to show you in the example that we were looking at the count of number of mean things that people said and show you what it would look like to check for zero inflation in that. So I'm coming back to example 3. This is page 2, in which I have a table here highlighting the idea that in the raw data, these are the means for each cell of my design. So it was a 2x3 combination where the 3 was 3 manipulated groups and 2 was 2 naturally occurring groups fully crossed with each other. And regardless of whether I fit a typical ANOVA, which is what this was the student was thinking she should do, or if I fit a count model, I end up with the same means. All of the inferences change with respect to the standard errors of those means and thus the differences across them. So a normal distribution assumes constant variance, whereas a Poisson assumes non-constant variance that's the same size as the mean, whereas a negative binomial assumes non-constant variance that exceeds the mean. But if I go back to, where are the pictures? Here we are. This is what I want to show you. This picture right here on the left, excuse me for a second as I cough. 1 second, I'm gonna shut. Okay. This picture right here on the left, I can't look at this picture and tell you whether or not I need a zero inflated model. If I just eyeball this picture, it kind of looks like I do, right? There's a big old pile of zeros. But the model assumptions are not about the marginal data. So this picture of marginally, like before I put predictors, if I literally just make a histogram of my outcome variable, that picture is not going to necessarily tell me if I need a zero inflation model. A picture like this can point me towards a family. So like if I look at this, I see the fact that it's bounded at 0, that I've got a big pile of zeros and some positive skewness, and that this is a count, they're only integers. That's going to point me towards a count family. But whether that count family should be Poisson, negative binomial, zero inflated versions of those, I don't know yet. Because the issue is how many of these zeros are predicted based on the predictors that I put in my linear predictor model. And so that is somewhat foreshadowed by breaking down the histogram by group here, to the extent that if I know what group you're in, I know how many zeros are expected, then some of that inflation is actually built into the model and it's not a problem anymore. So the question that we have to ask is, after controlling for all of the predictors that were put in the model, do we still have extra zeros that we need to worry about, in which case we would want to do either a zero inflation model or a hurdle to remove the zeros and put them into a different submodel altogether. So that's an empirical question that I answered in these data. Let me scroll to that section. So we did all of this before, comparing normal to Poisson to negative binomial. Negative binomial fit relatively best. It had a Pearson chi-square over degrees of freedom fit statistic that was close to 1, which is what we wanted. So now I'm asking the question on page 11 whether we still have extra zeros relative to what the negative binomial model predicts. So I'm going to try to fit a zero inflated Poisson and a zero inflated negative binomial to compare. So in Stata, the function that I'm using is called zip, ZIP, which is not zippity doo dah zippity a, it is zero inflated Poisson. So I'm taking off the stretchy factor and I'm adding in an inflation factor to see if that does a better job. And so otherwise, aggressive verbalizations is my outcome. Here's my linear predictor. So the 3 main effects and 2 interaction terms that differentiate my 6 possible conditions. The new thing is right here, inflate with underscore constant. What that means is add a zero inflation model, so allow there to be extra structural zeros, but don't put any predictors in it. Just give me an intercept. Because here's the logic. If the probability of being an extra zero is really, really, really small, I don't need that. It doesn't help anything. So it makes sense to just ask whether you have detectable extra zeros in the first place before you try to predict who they are. So I'm just fitting an empty inflation model with this. So in this package, it doesn't tell you distribution fit, unfortunately. It does give me the inflation model in Logits. So the probability of being an extra zero according to this Poisson model is the logit of minus 0.54. That corresponds to, here's the math, a probability of 0.37. So this is telling me that if I use a Poisson model for this outcome, after controlling for which group someone's in of the 6 possible conditions, I have a probability of being an extra zero of 37%. So that's still pretty high. That would be concerning if this model fit well. So I did the same thing in R. I had to look around to find a zero inflated Poisson, and I ended up using something called zero INFL, and that's within a package called PSCL. And no, I do not remember what that stands for, but I have a link on the class website to every package that I'm using so that you can look through it and know all the features that it has. So it comes up with the same estimate of the logit of the probability of being an extra zero that translates into a probability of 37.37. However, when I've tried to get the fit index of this, Pearson chi-square residuals over degrees of freedom, it's about a value of 2. So what this is telling me, the 2 means that I have twice as much variance in my residuals as what is expected based on a Poisson distribution, even after adding in zero inflation. So what this is telling me is that on the whole, a zero inflated Poisson does not fit this very well. I tried to do zero inflated negative binomial, and Stata blew up, meaning it would not converge, did not give me any output. I did get some output out of R, so I switched to dist equals neg bin for the count part, and link equals logit for the inflation part, is still the same. And it came up with a logit for the zero inflation model of negative 11. Without doing any math, how big is a probability that corresponds to a logit of negative 11, do you think? Or how small, should I say? Remember in logits, 0 corresponds to 50-50 probability. So what would negative 11 be in probability terms? Yeah, very, 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 very small. Definitely less than 0.5, 0.00000 something. And in particular, it is 0.00015. So after I add in the negative binomial stretchy factor that we already learned we needed, the probability of being an extra zero beyond what is already predicted by negative binomial is a tiny, tiny, tiny number. So that tells me that no, we don't need this. If the probability of being an extra zero is that small, we don't have any extra zeros that we really need to worry about. So we decided that was good enough. One thing that I found Stata users, by the way, that I thought was really cool, so I'm putting it in here, is a user-written routine called CountFit that does a lot of these comparisons for you. So I am using something called CountFit to keep the same linear predictor here, and I'm asking it to simultaneously estimate and compare the Poisson model, the negative binomial model, zero inflated Poisson. It would also do zero inflated negative binomial, but I knew that one blew up already, and so I didn't include it in this comparison. And it spits out a very helpful table here that describes the AIC and BIC across models and the differences. And it summarizes, I like this table, evidence. So is negative binomial regression model better than Poisson? Very strong evidence. Is zero inflated Poisson better than regular Poisson? Very strong evidence. So all of this is just reconfirming what we've already seen, that basically it looks like we could either have a zero inflation factor with a Poisson or a stretchy factor without zero inflation, but not both. And if I had to pick between the two, stretchy is better fit than just zero inflated Poisson. It also has this picture, which is how far off the predicted counts are. So we have the regular Poisson model is predicting way too many zeros. We have the regular negative binomial, which is the red line here, which is pretty close to zero. So that zero means that the prediction is accurate. There's no bias. And green is the zero inflated Poisson, which gets the zeros right, but still expects way too many ones relative to what we have in the data. So visually, the fact that this red line is matching zero for most cases means that it's doing a better job than its competitors in accounting for all of the skewness and potentially extra zeros. Doesn't look like we have any. So that gives me the same evidence that I did manually by going through the models one by one. Looks like we don't need an extra zero inflation. Let me see here, where'd my slides go? Let me see what else is in here. I think that's it, right? Yeah, okay. So I have a couple slides on where you can find different options for count stuff across software packages and how you could do that. I have a little bit of a summary about comparing models here. We talked about that. One last thing that I wanted to show you, just because I thought it was really cool, but I'm not going to expect you to do this, is what's known as a heterogeneous negative binomial. The idea of the stretchy factor being something that is in and of itself predictable. So this is heading towards the idea of building a linear model for why you have skewness in your data. Like, how do I predict the fact that I have different amounts of variance for higher counts than lower counts? So this GNB-reg thing allows you to predict the stretchy factor itself. So I fit the same linear predictor to try to do this, and I saw this result and I was like, uh-oh. So here's a pro tip, folks. No matter what your software tells you, it may say that it converged and everything is fine with no error messages. If you see something like a logit of -12 with a standard error of 23 and a confidence interval from -57 to 33, it has no idea what that parameter is. It's not really converged with respect to all of the individual parameters. So this indicates a great amount of instability. It's not able to figure out all the stuff at once. I simplified the model just to put a constant in to see if I needed anything more, and no. So took out the interactions, simplified it, didn't need it, didn't need it, didn't need it. So I just leave this in here in case this is something that's of interest of you, but I'm not going to require you to do this because I don't know how to do it in R. Last but not least, as usual, I have a sample results section for how you would write up these types of analyses. So I did this in a way that corresponds more to how I would try to publish it than how I would arrange it in a handout. So I have a whole, like the first paragraph is, what did we do? So this is my outcome, this is the model we're considering, this is how I indicated effect sizes, this is how I judged significance. Then I have this paragraph that describes the process of evaluating which conditional distribution I want to use. So I compared Poisson and negative binomial, compared the zero inflated versions to that, figured out which one was the most believable in terms of it fitting the data the best, and then I went into the pattern of results. So if the distribution doesn't fit, you wouldn't want to report those results at all because they're not trustworthy. So the process of figuring out which one to use, I put front and center and then described what happened using the chosen option. So then I have some words in here, and I would use the same sorts of tables and figures that are throughout the handout to illustrate the findings. The actual paper that these data were taken from is in the download folder as well, so that you can see what it looked like with a little bit additional complexity. There was some extra covariates and stuff like that. So it's not exactly the same model. It has extra stuff in it, but it's the same set of concepts. All right, there, blue sky. Mr. Microphone cooperating. Everyone still awake? There's some thumbs. Tuesday after spring break, that's impressive. I feel like I'm ready for a nap. If I take a nap at 3 o'clock, though, there's no going to bed tonight. Bad things happen. All right. Any questions before we call it a day? So you will get a chance to practice these count models in homework 4, which is down the road a couple of weeks. I will let you know as soon as that is available. I will also let you know when I have some new stuff to post on Thursday. I was hoping to add another type of model to it, but I don't know if I'm going to have time to do that between now and then, so we'll see. But I will have examples of how to do proportion correct kinds of outcomes, which is going to be using the binomial family, a new type of distribution starting then. All right, how about we end 5 whole minutes early? Yeah, thumbs up for that. All right, folks, let me know if you need anything. Office hours are tomorrow as usual, and I hope to see everybody Thursday. We're going to be on Zoom again because our classroom is being taken over by comprehensive exams, so we will be here. All right, thanks for being here, folks. See you then.